next speaker is Jitae, a postdoctoral fellow from the University of Kentucky. Welcome.
Okay, my name is Jitae, postdoc researcher at University of Missouri. I'm going to talk about the UAV-based stream velocity and discharge assessment under below conditions: LiDAR, photogrammetry, and PID technique. Oh, yeah. I'm working with Dr. Bing Wang at University of Missouri, and there's other collaborators in University of Missouri, and there's this project is funded by the Missouri Department of Transportation and also supported by Missouri Water Center. I'm gonna start with the introduction. This one of this study, and afterwards I'm going to show you the objectives of this study and the test will be done with the field and data analysis, research, and conclusion before. Okay. Conventionally, the hydraulic parameters like stream velocity and discharge are measured using in-situ instruments. In-situ instruments with station measurements like acoustic Doppler current profiler or the ACPs, or flow meter or step gauges. And these methods require physical deployments. They normally from bridges, boats, wading. They often measure under challenging flow conditions, like this you can see in the pictures. Using UAV, we can derive surface velocity and discharge without physical entering stream. So we are trying to measure the stream velocity and discharge using UAV. So we can capture high resolution data, even in hazardous or hard to reach locations. And we are going to integrate photogrammetry and LiDAR and the image-based the surface velocimetry. So we hope that the UAV methods provide safer and more effective measurements in the line coverage. So we want to develop a UAV-based workflow. You want to integrate the LiDAR and photogrammetry and particle image velocimetry. It's called PID. So we are going to measure the stream velocity and discharge to flood events. And we also want to calculate the UAV-based stream discharge using with the surface velocity of the earth stream velocity and without surface velocity. And lastly, we are going to compare the UAV-based discharge estimates with the USGS data. For field test, we conducted two different survey sites. The first one is Hinsing Creek, which is located 3 kilometers east of downtown Columbia. It's near the University of Missouri campus. And we surveyed June 5th this year. And the second site is Petai Creek. It's located 30 kilometers west of Columbia, Missouri. And we surveyed April 21st. You see the locations in red for Hinsing Creek and blue for Petai Creek. For stream survey, we use the Jitae IM350 showing in center picture. We use L2 sensor to measure the data, LiDAR data, and we also use the RPK base station to measure the LiDAR, and we also use the P1 camera sensor to measure the photogrammetry. You could see the LiDAR data and image data in the controller from the picture. So we conducted the same survey with the L2 sensor. L2 sensor is light for LiDAR data. L2 sensor is a high precision laser scanner mounted to the UAV. And it sends a related laser to the ground and it measures the return time so that they can detect the height of the objects on the surface and fronts. So on the left, you can see the height information from the LiDAR data. From there, you can calculate. We can build the terrain model, which is shown on the right. So you could see the this is the power line and this is the bridge. These gray parts are trees. So we are trying to remove those objects to get the ground information from the measurements. And we also we use the P1 camera sensor to get the orthophoto. We process the images to get the orthophoto. Orthophoto is a high resolution geo-reference images to the surface. And we are going to use the orthophoto together with the LiDAR data, so we can cross-check with the photo is true or not on the screen. And we did the PID measurements at the upstream of the bridge. We used smaller drum, Jitae and E. And this is red area is the area we took for the PID measurements. PID is particle image velocimetry, so we detect the particles on the surface of the screen, how they grow. So we take the video. The center figure shows the beam velocity of the particle movements. So we estimate the surface velocity by averaging those red colored dots. So we can get the velocity distribution across the channel. And then we use the both with the sonar sensor. And the center figure shows the measure the depth using these boards and sonar sensor. Sonar sensor gives the depth information. So we overlaid with a Google Map base map as base map. So you can see this overlap with the original channel. On the very right, the depth information, we calculate the depth information across the river. For data analysis, we estimate the discharge with our surface velocity, and data elevation model was generated from LiDAR data. So with that DEM model, we calculate the channel slope, how the river slope is, and then we apply the magnification to calculate the discharge using the cross-section area and hydraulic radius that we measure in depth measurements. And using surface velocity, we apply the velocity area method. We use the mean surface velocity field from UAV PID measurements. And we apply coefficients approach to calculate the depth area velocity. And then we apply the velocity area method to get the discharge. So this is a rating curve from the USGS website. And this grasshopper are the field measurements for 3 years. And blue cross is the mains measured features. And red cross is PID measured features. In Hinson Gray, you can see this right here is quite decent high flow. And in Petasarin Creek, this right here, it's quite higher than the field measured data. And you can also see those data fits quite well with the weighting curve, which the USGS provided at the websites. And both UAV based Manning's estimate and PID estimate are quite well aligned with the reference, which is the x-axis, is station discharge data, and this is Manning's discharge, and this is the PID discharge. It's well aligned with reference data. These are the PID measurements. These two are Manning's derived discharge, and the difference in Manning's basically are 41%, and in peptide is 27. Using PID is 33 and 18 in peptide. So PID shows really smaller difference from the reference values. It's about 18 to 33% compared to Manning's gives 27 to 41%. So we integrate the UAV workflow successfully under flood condition. We combine the LiDAR and photogrammetry and PID to estimate the stream velocity and discharge. The accuracy is about 18 to 33 using PID-based discharge estimation, and it's about 27 to 41% using Manning's method. So we hope this method provides rapid and safer flood assessments without in-channel measurements, and we hope to be it supplies the agency to estimate discharge for timely decision making. Right? This is I'm happy to take any questions.
Yeah, as a curiosity for the research, like from the area velocity method, which method did you use, like for mid-section or min-section method?
Can I hear?
For the area velocity cross-section measurement method, so did you use mid-section method or min-section method? Or you took average? I don't.
You're talking about the mean section of the river.
Oh yeah, I mean I'm talking about area velocity method. So that we use sometimes mid-section method or min-section method to calculate the discharge. Can you go there? Oh yeah, this one.
Yeah.
Did you use min-section method or mid-section method to calculate discharge?
Oh, we actually use mid sections.
Oh, mid-section. Oh, okay, yeah. So thank you so much.
Why do you think that the Manning seems like it's underestimating law?
Maybe it's a little bit higher.
Overestimating it? Why do you think is that?
Well, actually, we don't know why PID is lower. It's not so machines lower. But we are figuring out why PID. Yes, that's true. PID measurements are lower. But we do not know right now.
Yeah, okay.
So we are figuring out.
That's interesting.